In this video, we look at the concept of drift velocity and current density. So we'll look at drift velocity and current density. Inside a conductor, there are delocalized free electrons, as you can see here. These are what? Free electrons. These electrons do not move in a straight line because they collide with each other. The particles here collide with each other. The particles here will be ions, positive or negative ions, and the electrons here as well. Of course, we know that in a conductor there will be full of electrons in a conductor. So you see that free electrons here move in different parts. Okay, so free electrons move in different parts when there is no potential difference between the ends of this conductor. So you notice that there will be random motions. Okay, so and again the overall velocity in this conductor cancels out. So the velocity cancels out. So the velocity here is 0. But if we now apply potential difference between the ends, just as this, if we apply potential difference between the ends, okay, so you now notice that there will be an overall velocity in one direction. So there will be an overall velocity, as you can see here, there will be an overall velocity in one direction. So how do we now calculate this velocity? So we define current as the rate of flow of charge. So current is charge per unit time. So and this charge is the total number of charge. So if from here to here is the length of this conductor, for instance, here we take the conductor to be a wire. The conductor here is a wire. So this is the total charge that flows in this wire in this direction. So and this total charge can be represented as this. This is Qn. Okay, of course, if we consider this as equation 1 and consider this as equation 2, this can be written as the product of current and time, the total charge. So we can as well write it as this, where Q is the magnitude of each charged particle. Magnitude of each charged particle. And of course, for electron or proton, we have it as 1.6. How did we get this? Suppose there are n charges per unit volume. Suppose there are n charges per unit volume. This n charges per unit volume. Then the total number of charges that passes through this cross-sectional area. So this is cross-sectional area A. So the total number of charges, which I represented as capital N, that passes through this cross-sectional area of this wire per unit time is denoted as this, where the product of the cross-sectional area and length is being denoted as the volume. So this is the volume. The product of the cross-sectional area and the length is the what? Volume. So if this is the case now, we can now represent our total number of charge as Q equals Q N A L. So let's call this equation what? 3. So I have said that this is a definition of the volume. This is a definition of the volume. All right. Now, if we want to consider the derived velocity, that is the velocity with which the electrons are moving, of course we know the length. So how do we go about it? We know that velocity is Velocity is displacement upon time. Velocity is displacement upon time. So we call this now the derived velocity, and the displacement now is in terms of the length in this direction. So we have it as L upon T. So L here now is the product of the derived velocity and the time. So we can call this equation 4. If we replace equation 4 in 3, if we put equation 4 in 3, we now notice that Q now, which is the total charge that will pass through this cross-sectional area, okay, per unit time, will now be, this is Q N A. So instead of writing L, I'll write V dt. So this is equation 5. So this is the total number of charge that will pass through this. So if I now want to find the current, if I want to find the current from this equation 1, we define current as the charge per unit time. So Q, we have found it to be Q N A V dt upon T. So this cancels, so that we have that Q, this is N, this is A, and this is what? Vd. So this is the current that passes through this cross-sectional area. The current that passes through this cross-sectional area. So we have defined the derived velocity, and we have it. Of course, when we make V the subject of the formula here, we can have something like this. We can have that Vd equals, this is Q upon QNAT. So this is a formula for what? Derived velocity. You see, this is the total charge, this is the magnitude of each charge particle, this is the number of each charge particle, and this is the cross-sectional area. Then this is the what? This is the time. The same thing applies here. You notice that we can make, if current is QNAVD, we can find derived velocity by making it subject of the formula. This is I upon QNA. So there are so many ways you can manipulate this. So we have defined the concept of what? Derived velocity. Now let us look at the current density. Current density, which is the number 2 thing we are looking at now. Current density is defined as J equals current per unit cross-sectional area. So this is the definition of what? Current density. This is what? Current density. Current per unit area. So if that is the case, we now have this. The current is QNA VD. This is subscript D upon, this is area. We have now, this cancels. We have QNVD. So this is current density. This is what? Current density. Current per unit area. So in our next video, we shall be solving problem that will be utilizing the concept of current density and derived velocity. If you have enjoyed this video, give it a like, share it with your friends, and if you have not subscribed, subscribe for more video updates. Thank you so much.